Welcome to a lesson on applying the constant rate of change, linear equations, and functions. Previously, we had used a table and a graph to study what happens when quantities are related by a constant rate of change. What we had discovered is that a functional relationship between quantities is linear if the quantities are related by a constant rate of change. And we had used this constant rate of change to find other values in the table and also other values in a graph. Furthermore, what we had done is we had developed an equation that describes the relationship when quantities are related by a constant rate of change. So in this case, what we had is a constant rate of change of 3.6, and we had a reference input and output of 2.2 and 15.12 respectively. So what we're going to do is study this a little further today. So what we have learned is that one form of linear equation was that h, for example, representing the height of the water tank, was related by the constant rate of change times the quantity t minus reference input plus the reference output. And what we're going to do is study this further. So to determine the constant rate of change, which is abbreviated CROC, one way to look at it is from the constant multiple perspective of proportionality, where the change in output is equal to the constant rate of change times the change in input, or from the constant ratio perspective of proportionality, where the change in output over the change in input is the constant rate of change. So let's look at an example. Suppose there is an amount of water in the tank, and the height of water was increasing at a constant rate of 1.4 centimeters per minute. 2 minutes after the water began filling, the height of the water was 35.7 centimeters. So what we're going to do is let t represent the time elapsed since turning on the hose in minutes, and let h represent the height of the water in the tank in centimeters. The first question asks us is to describe the process for determining the height of the water in the tank when 7.3 minutes after the water began filling. It's asking us to show the work for each step of the process and to illustrate each step using a table or graph. What we're going to do first is look at it using a table perspective. So let's do that. So looking at the table, we know when 2 minutes have elapsed, the height of the water in the tank is 35.7 centimeters. And what we want to do is to figure out what is the height of the water 7.3 minutes after the water began filling. So let's see what we can use. First thing we'd want to do is find the change in time, which to do that you take 7.3 minus 2 to give us 5.3. So the change in time is 5.3. We'll use the constant rate of change to relate this. So we know that we're trying to find out what the current height of the water is. So we first need to figure out the change in height. So the change in height is 1.4 times delta t. That will determine change in height of the water. So 1.4 being the constant rate of change, and we know that the time is changed by 5.3 minutes. Doing that, multiplying those two together will give us the change in height, which is 7.42. So delta H is equal to 7.42. So that means that we are increasing 7.42 centimeters from 35.7 centimeters. When we do that, so we're taking the current height is the change height plus the reference height, which was that original height of water. And to do that, we take 7.42 plus 35.7. And then we get 43.12 centimeters. So according to that, the height of the water, when we have 7.3 minutes have gone by, the height of the water is now 43.12 centimeters. So now let's also look at what this would mean if we're looking at it from a graphical perspective. So what we're going to do is look at the graph. So again, we're starting with that reference point of 2, 35.7. Let's see how the individual steps correspond to what happens in the graph. So the first thing we know is that we change in time by 5.3 minutes, and that's as a result of subtracting 7.3 minus 2. We know that our change in height is 7.42, and that's a result of first taking 1.4 times that change in time, and that comes out to 1.4 times 5.3, which is 7.42. And then we know after that if you increase 5.3 minutes from 2, you're at 7.3 minutes, which is that first coordinate of 7.3. And the 43.12 is the result of taking 7.42, taking that change in height and plus that reference height of 35.7, adding the 7.42 plus 35.7 to give us 43.12, which is the y-coordinate, or in this case the h-coordinate, the output coordinate of the graph. So that's a little bit about it. Let's look at a different question. Next one is, let's say we want to create a linear equation that determines the height h of water in the tank t minutes after the water in the tank began filling. Be able to explain each piece of the formula. So that's what we're going to do. Let's first analyze what happens. The first thing we'd want to do is figure out the change in time. We would take whatever the current time is minus 2. In the example we did previously, 7.3 was that t. But what the idea is how would we generalize that if we don't know exactly what time we were advancing to? So to figure out the change in time, take whatever that current time is minus the reference time of 2. To figure out the change in height, we would take 1.4, which is that constant rate of change, times the change in time. But the change in time in this case is t minus 2. So we could use that knowledge to write another expression, which is 1.4 times t minus 2, and that's going to be delta H. Lastly, to figure out the current height, we take the change in height plus whatever the reference height was. In this case, our reference height was 35.7. And we're going to use the expression of whatever delta H is, change in height, to figure out our current height. So what this would mean is, without knowing what the time is necessarily, that H, the current height, is equal to 1.4 times the quantity t minus 2 plus 35.7. And if we were to use 7.3 in place of t, we would get exactly 43.12. But what's nice about the equation is that it will do it for any value of time. If you're given a time, it will find the corresponding height all at once. So our linear equation that determines the height h of water at tank t minutes after the water in the tank began filling is h is equal to 1.4 times the quantity t minus 2 plus 35.7. And height h is measured in centimeters. Now if you were to draw this line, let's say you were to put in a calculator. Now in this case, t represents the input and h represents the output. But if you were to do that, you would notice that the line that is graphed crosses through both points, which is exactly what we expected to happen. So that means we did it right. Now let's focus on this linear equation that determines the height. So if we're looking at the parts of the equation that have developed this, that 2 represents the reference input. And then this t minus 2 represents the change in input. Because one of the things that we want to be able to do is to explain each piece of that formula. So 2 represents the reference input, and then t minus 2 represents the change in input. Now that 1.4 does represent the constant rate of change, and if we're looking at the constant rate of change times the change in input, that represents the change in output. So what's left is to figure out what that 35.7 is, and that is the reference output. So if you're looking at the reference input and reference output, that would represent a coordinate graph called the reference point, and that's the point from which we are basing our predictions. So in this case, the reference point was 2, 35.7 from a graphical perspective. As we look at this, really the general template or the general equation is that if we were to, for any arbitrary constant rate of change, in this case the constant rate of change was 1.4, but to figure out the formula that equation that describes generically how to predict height given any time, if you know the constant rate of change times the quantity t minus the reference input plus the reference output, that would actually determine for a given time what the corresponding height of the water in a tank is. And so what it is those places of constant rate of change, reference input, reference output, are what you would replace given your particular situation. Now t minus the reference input will always calculate the change in input. The constant rate of change times the change in input will always calculate the change in output. And that change in output plus the reference output would calculate what your current output is. In this context, it represents the height of the water in the tank. So let's say we want to create a linear function that determines the height of the water in centimeters in the tank t minutes after the water in the tank began filling. See how that works. So first we have to figure out what the input is. The input is time in minutes, and the variable that's used to that is t. The output is the height of the water in the tank in centimeters. That's represented by h of t, because when the input is given in time in minutes, h is the name of the function that determines the height of the water in the tank in centimeters, and that output is represented by h of t. So to do this now, if we wanted to write a function rather than an equation, what you do is you say h of t, which is a function notation, that's equal to 1.4 times t minus 2 plus 35.7. So the expression on the right side is identical. It's just how we're interpreting, whether we're thinking a relationship as an equation or the relationship as a function. Will change our notation, whether we use h literally like it was before for an equation, or if we use h of t using function notation. Therefore, we're thinking about t as the input and then h of t as the output. So it's really more precise when we think of it from a function notation perspective. So if we're looking at it as a graph, you'll notice that this function graphs a linear relationship that crosses through the point 2, 35.7. But you will also remember that this very same line also went through 7.3, 43.12. So the point of what happens is, as long as the line crosses through any of the reference point and it has the same constant rate of change, any of these points could be used as a point of reference. So what this means is using this idea of the equation, we could create an equation that produces exactly the same line that crosses through both points, but using 7.3, 43.12 as a reference point. And analogously, in function notation, it will look awfully similar. It would just be h of t is equal to 1.4 times the quantity t minus 7.3 plus 43.12. So again, this means that we would end up with the exact identical line. In a future lesson, I'll explain why those both produce exactly the same line. Both the h is equal to 1.4 times t minus 2 plus 35.7, and the h equals 1.4 times t minus 7.3 plus 43.12. But as we study how this line goes, we also notice it crosses through the vertical axis. So as we do that, we'll studying the graph, it crosses through 0, 32.9. So that means that any point that's on the line would produce an equation that is true. So what that means is, for example, we could also write an equation which is h is equal to 1.4 times t minus 0 plus 32.9. That will produce an equation that goes through all three of those points because they are related by the same constant rate of change. And you notice that t minus 0 could be simplified to t because anything minus 0 is itself. So a more simple way to write that is h is equal to 1.4t plus 32.9. It turns out that many of our equations we use a reference point on the vertical axis, and that will lead to a very specific equation that is very useful in future lessons. We can also know that the function, the corresponding function, is h of t is equal to 1.4t plus 32.9. So again, we can see using an equation how to write it, and we can also see using a function how to write it. So if we're looking at a summary of what this lesson is about, and looking at one form of linear equation, is this idea of if you were using height of water as the output and t, the time elapsed a minute, is the input, we think of h is equal to the constant rate of change times quantity t minus the reference input plus the reference output. Now, written more efficiently, we could write the constant rate of change as Cronk, and that reference input and reference output, using the variables associated with the reference input and reference output. Sometimes you will see this represented as tref and href, because when t is the input variable and h is the output variable, then tref and href represent that reference input and reference output. And sometimes that's given in a table, sometimes that's given as part of the problem, or sometimes it's given as a graph. So let's also see what now to determine the constant rate of change, what would we use? Well, we know from earlier that the change in output is equal to constant rate of change times the change in input. And the constant rate of change is the change in output divided by the change in input. So that's how constant rate of change is determined, which is abbreviated CROC. How would this look like if we were using y's and x's? Y is typically the output and x is typically the input. So when we're looking at it, y would be equal to the constant rate of change times the quantity x minus x ref plus y ref. And again, here x is the input variable and y is the output variable. You will also notice that sometimes they will use a slightly alternate notation for CROC. They'll use y is equal to m times x minus x ref plus y ref. So you might be wondering what m represents. M is the variable used to represent the constant rate of change. And it's also called the slope of the line. So m and CROC are the same number. M is used usually for geometric contexts, but it will be, and thus it's called the slope of the line. But the number that's used for m and the number that's corresponding to the CROC, which is the constant rate of change, are the same number. It's just two different perspectives which lead to the same number. M is used more for geometric contexts. CROC is more used for application type problems. But the number will be the same, and the process used to determine it will be the same as well. So what this means is that if we were thinking relating the change in output to the change in input from the constant multiple perspective and the constant ratio perspective, let's see how that looks. It would be the change in output is equal to m times the change in input, because m and CROC are the same, and m is equal to the change in output over the change in input. So sometimes you will see slope is equal to the change in output over the change in input, which is what oftentimes is said in a geometric context. So this is a little bit of a taste of what is coming ahead as you're looking into future lessons. We will look more at the geometrical context of the constant rate of change, and oftentimes we will refer to this constant rate of change as the slope of the line. I hope you found this helpful.